Hello everyone, very good afternoon. Good afternoon. Okay, so am I audible, visible? Good afternoon everyone. Good afternoon. Good afternoon. Happy Makar Sankranti. Happy Makar Sankranti. Okay, so please let me know everything is fine. Audio, video is okay. Audio, video is perfect. Shall we start the session? Shall we start the session? All okay, na? Okay. Okay, so let's start the session, right? So in this particular session, we will try to solve PYQs question, right? Most expected PYQs, right? PYQs from where you will get the question in this year. So we will try to solve those PYQs. Okay, so let us start this session. So start from this PYQ. This is GATE 2009 PYQ for 2 marks, right? See this question. Consider steady state heat conduction across the thickness in a plain composite wall as shown in the figure, exposed to the convection condition on both sides. Okay, so this is a composite wall. This is a composite wall, right? And this composite wall is subjected to the convection boundary condition. So in this side, this is the left side of the wall. This is left side of the wall. This is right side of the wall. So left side of the wall, left side of the wall, fluid having convective heat transfer coefficient, that is Hi, and the temperature is T infinitive I. Right side fluid having convective heat transfer coefficient H0 and the temperature is T infinitive naught. Okay, so Hi is given, H0 is given, T infinitive I is given, T infinitive naught is given, K1 K2 is given, L1 L2 is given. In question, it is clearly mentioned, assume negligible contact resistance between the wall surfaces. The interface temperature T of the two walls will be. So this is a question. हाँ, इसमें आप केमिकल, इफ यू आर फ्रॉम द केमिकल बैकग्राउंड, ठीक है, तो आप केमिकल वाले भी कर सकते हो, ऐसी कोई दिक्कत नहीं है, राइट? इफ यू आर फ्रॉम द केमिकल बैकग्राउंड, राइट, you will attend this session also. Okay, so in this question it is clearly mentioned interface temperature, right? Interface temperature. So what is the interface temperature? So this is the interface of these two walls, right? This is the wall number 1, this is the wall number 1, and this is the wall number 2. Wall number 1 and wall number 2, for the wall number 1 and wall number 2, this is the interface. So what is the interface temperature? This is asked. In this side the temperature is 20 degrees Celsius, and in this side the temperature is -2 degrees Celsius. So this is series connection problem. So whenever you are getting such kind of problem, first draw the thermal circuit, right? Whenever you are getting such kind of problem, first draw the thermal circuit. So if you see here, right, in this side T infinitive I is given, that temperature is 20 degrees Celsius, and this side T infinitive naught, this temperature is given -2 degrees Celsius, -2 degrees Celsius. So definitely that heat transfer occurs from 20 degrees Celsius fluid to -2 degrees Celsius fluid. So this is the direction of heat transfer, right? So if you draw the thermal circuit here, this is the convection resistance of the fluid, this is the conduction resistance offered by the wall number 1, this is the conduction resistance offered by the wall number 2, and this is the outside fluid convection resistance. What is the temperature here? This temperature is T infinitive I, and this temperature is T infinitive naught. Let us consider interface temperature is Ti, right? Let us consider interface temperature is Ti. Now what is the convection resistance here? Let us consider this is the RTH H, right? or you can say, let us consider this is the RTHI. This is the wall number 1 conduction resistance. So we can write this is the L1 K1A, or simply you can write RTH, or you can write RTH1. This is wall number 1 conduction resistance, and this is the wall number 2 conduction resistance, right? And this is outside. This is outside convection resistance. This is outside convection resistance. Okay, now if you see here, we can write that Q dot, because see, T infinitive I is known, T infinitive not is known. We can calculate RTH easily. We can calculate RTH1, RTH2 and RTH naught. So simply we can write, if you perform the energy balance here, if you perform the energy balance, right, series connection energy balance, if you performed here, simply we can write this is T infinitive I minus T infinitive naught upon RTHI plus RTH1 plus RTH2 plus RTH naught. And what is the unknown here? That unknown is Ti. So we can write Ti minus T infinitive naught. We can write Ti minus T infinitive naught divided by this resistance plus this resistance. So this is RTH2 plus RTH naught. You can equate this to also, na, T infinitive I minus Ti upon this plus this. You can equate this to also. Okay, so can anyone tell me? T infinitive I is 20 degrees Celsius. T infinitive naught is minus 2 upon RTHI. What is the RTHI? That RTHI is 1 upon HI. So this is 1 upon HI is 20, right? RTH1, L1 by K1A. So L1 is 0.30. This is 0.30 upon K1, and K1 is 20. K1 is 20. So this is 20A plus RTH2. What is the RTH2? That is L2 by K2A. So L2 is 0.15 divided by K2A, that is 50. 50A plus this is 1 upon H naught. H naught is 50. This is 50A, right? And this is equal to Ti is unknown, right? This is minus 2 divided by this is 0.15 divided by 50A plus this is 1 upon 50A, right? So A is cancelled out from both the side. There is only one unknown, and that unknown is Ti. There is only one unknown, and that unknown is Ti. So you can calculate Ti directly from here. Again, you can calculate Ti directly from here. So what is the answer that you are getting? What is the answer that you are getting? What is the answer that you are getting? I think this, that answer is 3.75 degrees Celsius. 3.75 degrees Celsius. 3.75 degrees Celsius. Cross check this answer. 3.75 degrees Celsius. 3.75 degrees Celsius. If someone asks you find out this temperature, can you calculate this temperature also now? If someone asks you find out this temperature, let us consider this temperature is TL. If someone asks you find out the TL, you can calculate TL also now. If someone says find out this TR, you can calculate TR also now, right? So this is a one problem related to the series connection. So I hope you can understand the logic behind the series connection. Okay, now come to the next question. This is GATE 2009 PYQ, right? Now come to the next question. This is GATE 2008. This is GATE 2008 PYQ. GATE 2008 PYQ. Now see this question. A steady two-dimensional heat conduction takes place in the body shown in the figure below. the normal temperature gradient over surface P and Q can be considered to be uniform. The temperature gradient del T by del X at surface Q is equal to 10 Kelvin per meter. Surface P and Q are maintained at constant temperature as shown in the figure, while the remaining part of the boundary is insulated. The body has constant thermal conductivity of 0.1 watt per meter Kelvin. The value of del T by del Y and del T by del X at surface P is. Okay. So this diagram is given, right? And in this diagram, there are two surfaces, surface P and surface Q. So this is the surface P, this is the surface P, and this is the surface Q. In this question, it is clearly mentioned the surface P and Q are maintained at constant temperature, right? So surface P temperature is 100 degrees Celsius and surface Q temperature is 0 degrees Celsius. What is the question? At the surface P, that means at this surface, what is del T by del Y and what is del T by del X? This is the question, right? So what is my question here? My question is at surface P, what is del T by del X at surface P and what is del T by del Y at surface P? This is my question, right? And you have these four options. Now, if you see this question, right, these are the four options, right? These are the four options. Okay. Now, if you see this question, then if I ask you what is the del T by del X at surface P, can anyone tell me? At surface P, if I am talking about the surface P, so let us consider this is the surface P and this is the surface Q, and remaining part is insulated. Now it is clearly mentioned in the problem. Remaining part is insulated. That means there is no heat transfer from the remaining part. So if you see the surface P and surface Q, this is the surface P, and this is the surface Q, right? Surface P is maintained at 100 degrees Celsius, this is maintained at 100 degrees Celsius, and this is maintained at 0 degrees Celsius. Okay, now tell me, if I ask you one question, what is the del T by del X at surface P? If I ask you one question, del T by del X at surface P, and what is the del T by del Y at surface Q? Now try to answer this question first. What is the del T by del X at surface P? Okay, so if you see the surface P, there is no temperature change in the X direction. If you see the surface P, right? What is the temperature here? 100 degrees Celsius. 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 So at the surface P, temperature is not changing in the X direction. At the surface P, temperature is not changing in the X direction. So what is this value? This value is 0. Okay, fine. Now if you see the surface number Q, this is the surface Q. This surface Q is maintained at 0 degrees Celsius. So what is the temperature here? 0 degrees Celsius. 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 That means at the surface Q, temperature is not changing in the Y direction. So what is the del T by del Y at surface Q? That is 0. I hope you can understand this. Correct. Now del T by del X at surface Q is given. Del T by del X at surface Q is given. If you see this question, then see the temperature gradient del T by del X at surface Q is equal to 10 Kelvin per meter. This is given 10 Kelvin per meter. This is given. Correct. Now in the question, del T by del X at surface Q is asked. Actually in this question, del T by del X at surface P and del T by del X at surface, del T by del Y at surface, del T by, this is del T by this is del T by del Y at surface P. Del T by del Y at surface P. This is asked. Okay. Now, if you see the option, now del T by del X is 0. Del T by del X 0. See, this option is eliminated. Del T by del X is 0. So, this option is eliminated. Del T by del X is 0. So, this option is also eliminated. Now, you have two options, option B and option D. In option B, del T by del X is 0, and in option D, also del T by del X is 0. Okay, fine. Now, if you apply the energy balance here, now this is your system, correct? Now, this is your system. This is your system. So, if you apply the energy balance here, if you write the first law of thermodynamics, if you apply the energy balance here, energy balance, this is a steady state problem, it is clearly mentioned. This problem is a steady state problem, it is clearly mentioned. In this problem also it is mentioned, this problem is in this problem there is no internal heat generation. So simply you can write this is the rate of energy in plus rate of energy out. Rate of energy in is equal to rate of energy out. So rate of energy in occurs via conduction. This surface is maintained at 100 degrees Celsius. This surface is maintained at 0 degrees Celsius, and this is the conduction heat transfer. Conduction heat transfer occurs like this. So if I ask you what is the energy in, so that energy in is nothing but the conduction heat transfer, rate of conduction at surface P is equal to what is the energy out? Rate of conduction at surface Q. So simply we can write, right, this is minus K P, right, this is thermal conductivity, or thermal conductivity is constant, right? So simply you can write minus K AP, not del T by del Y at surface P is equal to, this is minus K AQ del T by del X at surface Q. Right, K and K is cancel out. Now what is the area normal to the, what is the area of surface P normal to the direction of conduction heat transfer? So this dimension is 1, and let us consider perpendicular to the monitor width is W. So 1 into W, right, this is 1 into W. So this is 1 into W into, now del T by del Y at surface P is asked. Del T by del Y at surface P is unknown. Now this is equal to area of surface Q normal to the heat transfer, normal to the conduction heat transfer, 2 multiplied by W. This is 2 multiplied by W. Now del T by del X at surface Q, and del T by del X at surface Q is given. Del T by del X at surface Q is given, that is 10. This is given, this value is 10. So from here simply you can say that del T by del Y at surface P is equal to 20 Kelvin per meter. 20 Kelvin per meter. So correct answer is option D. That option D is correct one. Right, correct option is option D. Option D is correct one. Is it clear to everyone? Correct option is option D. Now come to the next question. Come to the next question. Come to the next question. Now tell me what is the answer for this question. This is GATE 2014 question for 2 marks. A material P of thickness 1 millimeter is sandwiched between 2 steel slabs as shown in the figure below, a heat flux 10 kilowatt per meter square is supplied to one of the steel slab as shown. The boundary temperature of the slabs are maintained. The boundary temperature of the slabs are indicated in the figure. Thermal conductivity of the steel is mentioned, that is 10 watt per meter Kelvin. 1D steady state heat conduction. For this configuration, the thermal conductivity of the material P is. So this is the material P. This is the material P, and the thickness of this material P is 1 mm. Right, thickness of this material P is 1 mm. This thickness is 1 mm. Now tell me what is the answer. So this is purely series connection problem, right? This is purely series connection problem. So whenever you are getting problem based on the composite wall, first draw the thermal circuit. Right, whenever you are getting problem based on the series connection or parallel connection, first draw the thermal circuit. So if you draw the thermal circuit, this is the conduction resistance of the steel, this is the conduction resistance of the material P, and this is the again conduction resistance of the steel. Here the temperature is 500 Kelvin. Here the temperature is 360 Kelvin. Correct, na? And this is the conduction resistance of the steel. And since there is an identical condition, so we can write this is also a conduction resistance of the steel. And this is the conduction resistance of the material P. Right? In this question, flux is given, right? That heat flux is given, that is 10 kilowatt per meter square. That means in this question, Q dot by A, that is nothing but the flux, that is given 10 kilowatt per meter square. So if I ask you what is the Q dot here, if I ask you what is the Q dot, what is the conduction heat transfer from this composite wall, so simply we can write that Q dot is equal to this temperature is known, na? T1 minus T2 divided by RTH equivalent, and this is a series connection problem. So RTH steel plus RTH of material P, conduction resistance of the steel plus conduction resistance of material P plus conduction resistance of steel. Right, both the steel are at identical condition, right? Thickness is same, thermal conductivity is same. So simply we can write this is nothing but the T1 minus T2. So this temperature is 500 minus 360 upon this is 2 times of L by Ka of steel plus this is L by Ka of material P. L you can say, thickness you can say, delta you can say, no issue. Right, so Q dot is equal to this is 500 minus 360, so this is 140, right? 500 minus 360, so this is 140. 2 multiplied by, not do one thing, take 1 by A common from the denominator. So this is Q dot by A, and this is equal to 142 multiplied by, this is 20 mm, so this is 0.02 divided by thermal conductivity of the steel, that is mentioned 10 watt per meter Kelvin, plus thickness of material P, that is 1 mm, so 0.001 divided by thermal conductivity of material P is unknown, and this Q dot by A, this is mentioned in the problem, that is 10 kilowatt per meter square. So this is 10 into 10 to the power 3 watt per meter square. Now solve this. So what you are getting, that Kp, thermal conductivity of material P, this is equal to 0.1 watt per meter Kelvin. Everyone getting this? Now tell me, everyone getting this? 0.1 meter per Kelvin. Everyone getting this? 0.1 watt per meter Kelvin. Okay, can you calculate the temperature drop in the material P also? Can you calculate the temperature drop in material P? If in the same problem, if someone asks me what is the, in the same problem, if someone asks me what is the temperature drop at material P, temperature drop at material P, can you calculate this also? If someone asks me what is the temperature drop at material P, temperature drop at material P, so temperature drop at material P, so here the temperature is T1, here the temperature is T2. Let us consider this temperature is T3 and here the temperature is T4. So what is the temperature drop at material P? That is T3 minus T4. Now tell me what is T3 minus T4. Simple na? It is simple na? T3 minus T4. T3 minus T4. So flux is given. Right? Flux is given. Flux is given. So Q dot, if you apply the energy balance, again simply you can write, this is a series connection problem. So we can write this is T3 minus T4. T3 minus T4 divided by this is conduction resistance of material P. Conduction resistance of material P. Right. Now this is equal to, this is T3 minus T4 upon RTHP. So this is nothing but the thickness is 1 mm, correct? So 0.001, this is 0.001, this is L divided by Kp. Kp you already calculated, this is 0.1 into area. Now do one thing, cross multiply with 1 by A. So this is T3 minus T4 divided by, this is 0.001, 0.1. Now this is 10 into 10 to the power 3. Now tell me what is T3 minus T4. Now tell me what is T3 minus T4. What is T3 minus T4? That T3 minus T4 is 100. That T3 minus T4 is 100 degrees Celsius, you can say, because ultimately this is the temperature difference. Ultimately this is the temperature difference. So you can say T3 minus T4 is 100 degrees Celsius or 100 Kelvin. Okay, now see the next question. Okay, this is a gate 22. This is gate 22 problem for 2 marks. मैं बढ़िया हूँ आदर्श, आप कैसे हो? हैप्पी मकर संक्रांति, हैप्पी मकर संक्रांति. Now see this question. This is gate 2022 problem. This is a problem of non-uniform internal heat generation. So there is a rod. There is a rod of thermal conductivity. Let us consider that is K. Uniform thermal conductivity is there. One end x is equal to 0 is insulated, and the other end x is equal to L is exposed to flow of air at a temperature T infinitive with a convective heat transfer coefficient H. The cylindrical surface of the rod A is insulated so that the heat transfer is strictly along the axis of the rod. The rate of internal heat generation per unit volume inside the rod is given. Right, so this is a heat generation in the rod. So this heat generation in the rod is a function of x. So this is problem of non-uniform internal heat generation. The steady state temperature at the mid location of the rod is TA. What will be the temperature at the same location if the convective heat transfer coefficient increases to 2H? And you have this 4 option. You have these 4 options. Okay, so first draw the rough diagram. First draw the rough diagram. In this question, there is a rod, right? There is a rod like this. There is a rod like this. Try to understand this problem, no? I know you know the answer, but try to understand the concept behind this problem. This is the rod, right? This is the rod. Right? Now, see, surface is insulated, x is equal to 0 is also insulated. This is x is equal to 0. This is x is equal to L. And at the mid location, that means at x is equal to L by 2, at x is equal to L by 2, the temperature is TA. So basically this is the axial direction and this is L by 2. Here the temperature is TA. When the temperature is TA? When this fluid having convective heat transfer coefficient H. When the convective heat transfer coefficient is H, when the convective heat transfer coefficient is H, that means when H1 is H, then the mid temperature is TA. Then the mid temperature is TA. When the temperature is, when H1 is H, mid temperature is TA. Now question is when H2 is 2 times of H, when the convective heat transfer coefficient is 2 times of H, then what is the mid temperature? What is the mid temperature? This is the question. This is the question. Okay, so first try to find out the temperature variation in this rod is dependent on this H or not, right? First try to find out the temperature variation with respect to X, because in this problem temperature only changes with X, because this problem is a one-dimensional steady state. This problem is one-dimensional steady state problem. So first try to find out in this particular problem the temperature changes with respect to X. That's okay, but that depends on this H or not. Try to find out this. If you will find this, definitely you can comment on the mid temperature. Definitely you can comment on the mid section temperature. Okay, now this is a cylindrical this is cylinder problem, right? So if I write general heat conduction equation, so in the axial direction, this is nothing but we can write this is d square T by dx square, because thermal conductivity is constant, na? This is Q dot G by K is equal to 0. This is the governing equation. This is the governing equation for this problem. This is the governing equation for this problem. Now d square T by dx square is equal to, now this is minus 1 by K. Now what is the Q dot G? That Q dot G is given, that is cos 2 pi x by L. Cos 2 pi x by L. Cos 2 pi x by L. So ultimately what is my objective? My objective is find this temperature variation with respect to X. What is my objective? My objective is find the temperature variation with respect to X. So temperature, you want to find out the temperature variation with respect to X, integrate this equation 2 times. So integrate first, integrate once. Integrate once. So if you integrate once, what you are getting, dt by dx is equal to, this is minus 1 by K, and integration of cos is sine, this is sine 2 pi x by L upon 2 pi L, correct, plus there is an integration constant, that is C1. Okay, can we find out this integration? Can we find out this integration constant C1? Yes, absolutely we can find out. So for calculation of this C1, we need a boundary condition. So it is clearly mentioned in the problem that X is equal to 0 is insulated, x is equal to 0 is insulated. There is no conduction heat transfer at x is equal to 0. So at x is equal to 0, rate of conduction is 0. So simply we can write minus Ka dt by dx is equal to 0. K is not equal to 0, A is not equal to 0, therefore dt by dx is 0. So this is the first boundary condition. At x is equal to 0, the dt by dx is 0. This is first boundary condition. So at x is equal to 0, dt by dx is 0. So what is the C1? At x is equal to 0. So sin 0 is 0. At x is equal to 0, dt by dx is 0. So C1 is 0. At x is equal to 0, that dt by dx is 0. So C1 value is 0. C1 is 0. Right. So what you are getting, that dt by dx, that dt by dx is equal to, dt by dx is equal to, dt by dx is equal to minus 1 by k, or this is minus L by 2 pi k. Correct na? Minus L by 2 pi k. Minus L by 2 pi k sin 2 pi x. Sin 2 pi x by L. So this is the dt by dx. This is the dt by dx. Correct? Now see. Now this is the equation number A. Let us consider this is the equation number A. So what is my objective? Temperature variation with respect to x. Find out temperature variation with respect to x. Now integrate once again. Integrate once again. Integrate once again. So if you integrate once again, what you are getting? The T of x is equal to, this is minus T of x. This is minus L by 2 pi k. Right. This is cos, integration of sine, that is minus cos. Na? So this is plus cos 2 pi x by L upon, this is, cos 2 pi x by L upon 2 pi L plus another integration constant, that is C2. So simply we can write the T of x is equal to, this is L square upon 4 pi square k, and this is cos 2 pi x by L plus C2. Right. This is the equation number B. This is the equation number B. Okay. Now try to find out the C2. Now see, if you see at x is equal to L, can we say at x is equal to L, if you perform the energy balance at x is equal to L, whatever the conduction is there, that is equal to the convection. At x is equal to L, see here, at x is equal to L, whatever the conduction occurs at x is equal to L, that is equal to the convection. So we can write at x is equal to L, that conduction heat transfer is equal to convection to the fluid. Convection to fluid. Now see, we can write this is minus KAC, that dt by dx at x is equal to L. Now this is equal to, this is H into A, and let us consider at x is equal to L, the surface temperature is TW. Let us consider here the temperature is TW. So at x is equal to L, we can say whatever the conduction is there, that is equal to convection. Now see this expression, see the equation number A. If you see the equation number A, it is very much clear. At x is equal to L, the dt by dx is 0. If you see this expression, then it is very much clear. At x is equal to L, the dt by dx is 0. So at x is equal to L, the dt by dx is 0. So this term is 0. At x is equal to L, this term is 0. So this term is 0. Therefore, TW is equal to T infinitive. TW is equal to T infinitive. Now, if you put here, at x is equal to L, the T is equal to TW is equal to T infinitive. Now, from here you will get the C2, right? So this is T infinitive. This is T infinitive is equal to L square upon, this is 4 pi square K, and this is cos 2 pi x by L plus C2, or at x is equal to L, correct na? So at x is equal to L, right? At x is equal to L, T infinitive, L square by 4 pi square K, right? Cos 2 pi is 1, correct na? Cos 2 pi is 1, correct na? Cos 2 pi is 1, correct na? cos 2 pi is 1, right? Cos 2 pi is 1, yes, right? Now this is C2. Now see this equation, see this equation and this equation, right? In this equation there is a h. If you see this equation, right, if you put here, right, you can calculate C2 from here. C2 is equal to something T infinity minus L square by 4 pi square K, right? The C2 is equal to T infinity minus L square by 4 pi square K. Now put here, and if you see this equation, temperature variation with respect to x, there is no h term. If you see this equation, equation number B, in the equation number B there is no h term, and since the temperature variation is not a function of h, and since the temperature variation is not a function of h, that's why if you double this convective heat transfer coefficient, there is no change in the mid temperature. And why this happen? Because of this variation, right? If you see the dt by dx, now if you see the dt by dx, this is the dt by dx, dt by dx is 0 at x is equal to L. That's why TW is equal to T infinity. If there is another function, definitely there is a, if there is another function, then might be possible there is a h term is present in the temperature variation with x. Are you getting my point or not? Are you getting my point or not? क्या आपको ये बात समझ में आ रही है कि अगर मान लीजिए यहाँ पे जो हीट जनरेशन का जो फंक्शन है कुछ और होता, if there is any other function, so might be there in this dt by dx. If you calculate dt by dx at x is equal to L, dt by dx at x is equal to L, the h term may be there, right? Ultimately you are equating the conduction heat transfer is equal to convection heat transfer. If dt by dx term is present, then definitely if you calculate the TW, if you calculate TW, let us consider this dt by dx is 0. Let us consider this dt by dx is 0. Let us consider this dt by dx is 1. Let us consider this dt by dx is 1. This dt by dx is 1, let us consider. And if you calculate this TW, so what you are getting? Minus Ka upon HA plus T infinity. If let us consider this dt by dx at x is equal to L is 1. So what you are getting? You are getting minus Ka is equal to HA TW minus T infinity, right? A and A is cancelled out. So this is minus K by H plus T infinity is equal to TW. So definitely in this expression, H is present, definitely. And in this expression, if H is present, so definitely the mid temperature is function of H. Are you getting my point? So this play very important role. So I hope you can understand this. अभी किसी ने ऊपर बोला था ना क्या लॉजिक से हम ऐसा बता सकते हैं क्या? ठीक है, आई थिंक किसी बच्चे ने ऊपर ये किया था. सर इन दिस क्वेश्चन इवन लॉजिकली वी कैन से सिंस TA mid temperature it will not dependent on the convective heat transfer coefficient, but the question is why it is not dependent on the convective heat transfer coefficient, right? Why it is not dependent on the convective heat transfer coefficient? It is not dependent on the convective heat transfer coefficient because of this, okay. So I hope you can understand. This is very beautifully framed question actually. This is GATE 2022 problem, very beautifully framed question. So I hope you can understand each and every point related to this question. So what is the answer for this question? Answer of this question is definitely in this case, Definitely that answer is C. Definitely in this case that answer is C. C is the correct one. Definitely. Okay, now come to the next problem. Again, this is GATE 2022 problem for 2 marks. Now see this question. This is GATE 2022 problem for 2 marks. Again, this is very beautifully framed problem. ए कब होगा नहीं बता सकते ना, ए कब होगा कैसे मैं बता दूं ए कब होगा, ऐसे कैसे मैं बता दूं ए कब होगा, वो तो डिपेंड करेगा ना कि आपको जो हीट जनरेशन है वो हीट जनरेशन का जो फंक्शन है वो कैसा दिया है, अकॉर्डिंग टू दैट वी विल आंसर ना. Right, okay, now come to the next problem. Okay, see this question. Consider steady state one dimensional heat conduction in an infinite slab of thickness 2L. Okay, the thickness is 2L. Correct. L is equal to 1 meter as shown in the figure. The conductivity of the material varies with a temperature Sk is equal to C into T, where C value is 2 watt per meter Kelvin square. There is a uniform internal heat generation. Okay, there is a uniform internal heat generation, that is 1280 kilowatt per meter cube in the slab. Both phases are maintained at 600 Kelvin. Yes, then the temperature at X is equal to 0, and where X is equal to 0 at the mid plane. At the mid plane at X is equal to 0. At the mid plane X is equal to 0. Okay. Now this is not a standard problem, right? In this particular problem, this particular problem is not a standard problem, right? Because this is a uniform heat generation problem. This is a uniform heat generation problem. What is my standard problem? What is my standard problem? If there is a uniform heat generation, 1D, steady, uniform heat generation, and thermal conductivity is constant, that is my standard problem. But in this question, steady state is there, one dimensional is there, uniform heat generation is also there, but in this problem thermal conductivity is not constant. In this problem thermal conductivity is function of temperature. So to solve this problem, start from our Brahmastra. And what is our Brahmastra? That is general heat conduction equation. That is our Brahmastra. So whenever you are getting non-standard problem, then start from your Brahmastra, and that is nothing but the general heat conduction equation, right? So we have the general heat conduction equation. We have the general heat conduction equation in Cartesian coordinate system. And what is the general heat conduction equation? Right, that is del by del x, del by del x, and that is k del t by del x plus q dot g is equal to 0, right? Because this problem is a 1D, steady uniform internal heat generation, uniform internal heat generation plus thermal conductivity is function of temperature. For this is the general heat conduction equation, right? Now see, we can write this governing equation in this form also, no? This is dt by dx, because this is a one dimensional problem, so your partial derivative is converted into total derivative, correct? Or simply this is d by dx, this is k, dt by dx is equal to minus q dot g, Now integrate this, So if you integrate once, if you integrate once, what you are getting? You are getting K dt by dx, right? If you are integrating once, K dt by dx is equal to this is minus Q dot Gx plus C1. And K is equal to 2t. That K is equal to 2t. K is equal to tt. Right? C1 is the integration constant. C1 is the integration constant. Okay, fine. Okay, now can you calculate C1? Can you calculate the C1? Can you calculate the C1? For calculation of C1, we need a boundary condition. So what are the boundary condition in this particular problem? What are the boundary condition? If I ask you, how many boundary conditions are you able to see in this problem? Are you able to see the boundary condition? Boundary conditions are always present in the problem. Boundary conditions are as per the problem. Boundary conditions. So what are the boundary conditions in this particular problem? So first boundary condition is definitely at x is equal to plus L, T is equal to 600 Kelvin. This is the first boundary condition. What is the second boundary condition? The second boundary condition is at x is equal to minus L, the T is equal to 600 Kelvin. This is second boundary condition. What is third boundary condition? The third boundary condition. This is a symmetric problem or not? This problem is a symmetric problem or not? This problem is symmetric problem or not? Yes, this problem is a symmetric problem. Absolutely. This problem is symmetric about the mid plane. Symmetric about the mid plane. So if you draw the temperature profile, right? If you draw the temperature profile, then you can easily see at x is equal to 0 that dt by dx is 0, because this problem is symmetric. So whenever you are getting symmetric condition in a problem, right? Whenever you are getting symmetric condition in a problem, use that symmetric condition. Your problem become very easy, or your solution become very easy. Whenever in a problem there is a symmetric condition, use that symmetric condition, right? Your solution is become very easy, right? So at x is equal to 0, the dt by dx is 0. Now x is equal to 0, dt by dx is 0. See, if we apply this boundary condition at x is equal to 0, that dt by dx is 0, then what is the C1? That C1 is equal to 0. See, that C1 is equal to 0. Sir, can we use these two boundary conditions, 1 and 2? Yes, you can use these two boundary conditions also, no problem, right? Sir, can we use these two boundary conditions? Yes, you can use these two boundary conditions also, no problem, no issue. Ultimately, you are getting the same answer, no problem, no issue. But to make the calculation easy, to make the solution easy, right, I am using these boundary condition first. Okay, now what I am getting, this is 2t dt by dx is equal to 2t dt by dx is equal to, this is minus q dot g minus q dot gx. Right, now separate the variables. So if you separate the variables, this is 2t dt, this is minus q dot g x dx. Now integrate both sides. Now integrate both sides. So if you integrate both sides, this is 2t square by 2 is equal to, this is minus q dot g x square by 2 plus another integration constant, that is C2. Right, now 2 and 2 is cancel out. Now for calculation of C2, now you can use this boundary condition, either this or this, either 1 or 2. So any one you can use, right? So at x is equal to plus L, T is equal to, let us consider that is TW, right? So at x is equal to L, T is equal to TW. So this is TW minus q dot g L square divided by, this is 2 plus C2. Now calculate C2 from here. So TW is 600 Kelvin is equal to minus q dot g is 1280 into 10 to the power 3 into L square. L value is 1. So this is 1 divided by 2 plus C2. So from here you can calculate C2. So can anyone tell me what is the C2? Can anyone tell me what is the C2? What is the C2? Can anyone tell me what is the C2? What is the C2? Now, once you know the C2, you have this equation, T square is equal to minus Q dot G x square by 2 minus Q dot G x square by 2 plus C2. Now tell me what is C2? The C2 is this is a square, no? Square. C2. Yes, it is a square. Yes, it is a square. Now tell me what is C2? And once you know the C2, you can calculate the temperature at x is equal to 0. So at x is equal to 0, that let us consider the T is equal to Tc. So this is Tc square is equal to C2. So that Tc is equal to, this is root over C2. At x is equal to 0, the T is equal to Tc. So the Tc square is equal to C2. So Tc is equal to root over C2. I think this C2 is 10 to the power. I think that C2 is equal to 10 to the power 6. Am I right? That C2 is 10 to the power 6. Am I right? C2 is 10 to the power 6. C2 is 10 to the power 6. Since C2 is 10 to the power 6, so Tc is 10 to the, this is 1000 Kelvin. Tc is 1000 Kelvin. Yes, absolutely. So Tc is 1000 Kelvin. So correct answer is 1000 Kelvin is correct. Okay. Now see this question. This is GATE 2019 problem. Now see this question. This is GATE 2019 problem. GATE 2019 problem. So there are 3 slabs joined together as shown in the figure. There is no thermal resistance at the interface. The center slab experiences a non-uniform internal heat generation with an average value of 10,000 watt per meter cube. Left and right slabs have no internal heat generation. All slabs same thickness, same thermal conductivity, and that is 5 watt per meter Kelvin. The two extreme faces are exposed to the fluid with heat transfer coefficient 100 watt per meter square Kelvin and bulk temperature 30 degrees Celsius. Heat transfer in the slab is assumed to be one-dimensional steady and all the properties are constant. If the left extreme face temperature T1 is measured to be 100 degrees Celsius, then what is the right extreme phase temperature T2 is? What is the right extreme phase temperature T2 is? Now first tell me, this problem is a symmetric problem or not? Right, there are 3 slabs, slab 1, slab 2, slab 3, and mid slab there is a non-uniform internal heat generation, and the average value of heat generation is mentioned, that is 10,000 watt per meter cube. This is a symmetric problem or not? Tell me first. So answer is this is not a symmetric problem. Answer is this is not a symmetric problem. If this is a symmetric problem, then what is the temperature here? Tell me, if this is a symmetric problem, then what is the temperature here? In this question, what is asked? What is asked? The left extreme phase temperature. That means T1. Here the the right extreme phase temperature. The right extreme phase temperature, that is T2. So right extreme phase temperature. This is the right extreme phase, and here the temperature is T2. Here the temperature is T2. Now tell me, if this is a symmetric problem, then what is T2? If this is a symmetric problem, then what is the T2? The T2 is 100 degrees Celsius. The T2 is 100 degrees Celsius. The T2 is 100 degrees Celsius. Right? Okay. Now come to the one very important line. Very important line. And what is that line? The line is the center slab experiences non-uniform internal heat generation. Focus on this line. Non-uniform internal heat generation. Non-uniform internal heat generation occurs at the center slab, and the average value of heat generation, that is mentioned 10,000 watt per meter cube. So this is the average value of heat generation. Actually, in this slab, the heat generation is non-uniform. What is the meaning of that? Right. Let us consider here the heat generation is. 100. At this point, the heat generation is 1000. At this point, heat generation is 500. At this point, heat generation is 300. At this point, the heat generation is 200. Like that. So actually, in this problem, the heat generation is non-uniform. And since heat generation is non-uniform, that's why this problem is not a symmetric problem. This problem is not a symmetric problem. This problem is an unsymmetric problem. And since this problem is an unsymmetric problem, so here the temperature is not 100 degrees Celsius. That is different from the 100 degrees Celsius. Is it fine? Is it clear to everyone? Now tell me, if in this question that instead of non-uniform, uniform is mentioned. Instead of non-uniform, if uniform is mentioned. Instead of non-uniform, if uniform is mentioned, then yes, your answer is correct. Here the temperature is 100 degrees Celsius. Yes, your answer is 100 degrees Celsius. Is it fine? Okay. Now see here. So what is the average value of heat generation in the slab, in the mid slab? Let us consider this is the slab number 1, this is the slab number 2, and this is the slab number 3. So what is the heat generation? What is the average value of heat generation? Let us consider that is Q dot G. So that Q dot G, that is mentioned, that is 10,000 watt per meter cube. And if I ask you what is the total heat generation, so this is simply, this is Q dot multiplied by volume, the Q dot G multiplied by volume. So whatever the heat generation occurs, right, whatever the heat generation occurs, right, that some part of that heat generation is propagated in this direction and some part is propagated in this direction. Let us consider in this direction heat transfer is Q dot 3, and in this direction the heat transfer is, let us consider this is Q dot 1. Towards the slab 1, the heat transfer is Q dot 1, and towards the slab 3, the heat transfer is Q dot 3. Now if you apply the energy balance, if you apply the simple energy balance, can we say that total heat generation, that is equal to Q dot 1 plus Q dot 3. That Q dot 1 plus Q dot 3. Right. What is the temperature here? Let us consider here the temperature is T2. Now what is the Q dot 1? Can I write Q dot 1 is equal to, this is H into A into, right, H into A into, this is 100 minus 30. Can I say that Q dot 1? The Q dot 1 is equal to HA 100 minus 30, can we say? What is the Q dot 2? Sorry, Q dot 3. Q dot 3, that Q dot 3 is, this is H into A, and this is T2 minus 30. T2 minus 30, right? Now see. So that Q dot G, that is 10,000 into volume. So A multiplied by thickness, that is 1, is equal to Q dot 1. So this is H. H value is 100 into A into 100 minus 30, this is 70 plus Q dot 3. This is H. H value is Q dot 3. H value is 100 into A into, this is T2 minus 30. Right? A value is cancel out. Right? This is 10,000. Right? This is 10,000 is equal to, right? Or do one thing. 100. So this is 100 is equal to 70 plus T2 minus 30. Right? 100 minus 70, that is 30. So T2 value is 60 degrees Celsius. The T2 value is 60 degrees Celsius. Now tell me, everyone getting this? T2 value is 60 degrees Celsius. T2 value is 60 degrees Celsius. Is it clear? Okay, now if someone asks me, find out this temperature, are you able to find out this temperature? What is the temperature here? What is the temperature here? What is the temperature here? If someone asks me, find out the temperature at the interface of wall 1 and wall 2, are you able to find out this temperature? Are you able to find out this temperature? Are you able to find out this temperature? The interface temperature, interface of wall 1 and wall 2. So draw the thermal circuit. So if you draw the thermal circuit, this is the convection resistance, and in the wall there is no internal heat generation. This is the conduction resistance in the wall number 1. What is the temperature here? This temperature is T. This temperature is, let us consider this temperature is T1. Let us consider this temperature is T1. No, here it is T1. Na? So let us consider this temperature is T1 dash. Here the temperature is T1 dash. What is the temperature here? This temperature is 30 degrees Celsius. This is the convection resistance and this is the conduction resistance in the wall number 1. Right, this is the convection resistance and this is the conduction resistance of wall 1. This is the convection resistance and this is the conduction resistance of the wall 1. And this is nothing but the Q dot 1. Now Q dot 1, or simply you can write that is T1 dash minus 30. See, if you apply the energy balance, we can write T1 dash minus 30, divided by, this is 1 upon H, that H is 100, plus this thickness is 1, so 1 upon delta by K. And what is the thermal conductivity? The thermal conductivity is 5 watt per meter Kelvin. So this is 5A is equal to is equal to, you can say T1 dash minus T1, or you can say simply not T1 dash, T1 dash is here, na? So you can say 100 minus 30, you can say that 100 minus 30 upon 1 upon 100A, 1 upon 100A. So K value is given, na? All slabs having thickness 1 and the thermal conductivity of the each slab is equal to 5 watt per meter Kelvin, na? Slab thermal conductivity is given, na? So can you calculate T1 dash here? Can you calculate T1 dash here? Yes, 1500 degrees Celsius. 1500 degrees Celsius. 1500 degrees Celsius. Similarly, if someone asks you find out the temperature here, let us consider this is the T3 dash. T3 dash. If someone asks you find out this T3 dash, T3 dash, are you able to find out this T3 dash? Are you able to find out this T3 dash? Are you able to find out this T3 dash? Right. Again, draw the thermal circuit. Again, draw the thermal circuit. So this is the conduction resistance of wall 3, and this is the convection resistance. Right. What is the temperature here? This temperature is T3 dash. What is the temperature here? This temperature is 30. What is the temperature here? This temperature is 60. So can you calculate T3 dash? Yes, we can calculate T3 dash also. Yes, you can calculate this also, na? Q dot conduction is equal to Q dot convection. Yes, you can calculate that also, yeah, no problem. That conduction is equal to convection. Conduction is equal to convection. You can find out from there also. Conduction is equal to convection. Ultimately, that is a concept of series connection, na? Okay, so I hope you can understand this problem. Fine. Now come to the next problem. Okay, now this is gate 2024 problem. This is gate 2024 problem. Gate 2024 problem. See this question. A plain solid slab of thickness L shown in the figure has thermal conductivity K that varies with spatial coordinate x as K is equal to A plus BX. So thermal conductivity is not constant in this problem. Thermal conductivity variation is given K is equal to A plus BX. A and B are positive constant, right? A and B are positive. A, B greater than 0, positive constant. And here the temperature is T at x is equal to 0. Temperature is 0 Kelvin, and here it is T naught. The slab has no internal heat generation, one dimensional. Which one of the following plots qualitatively depicts, qualitatively, not quantitatively, qualitatively, right? Which one of the following plots qualitatively depicts the steady state temperature distribution within the slab? Okay, and you have these four options. You have these four options. अरे नहीं नहीं, ऐसा कुछ भी नहीं है. वाई यू आर थिंकिंग लाइक दिस? यार देखो, अच्छा ठीक है, ऐसा कुछ नहीं है उसमें, मतलब उस चीज को इतना ज्यादा प्रेशर खुद के ऊपर नहीं लेना है, ठीक है। अभी आपको ये होना चाहिए कि यार जितना भी टाइम है ना, जितना भी टाइम है उस टाइम में अपना 100% देना है, दैट्स इट, ठीक है यार। हम सभी वो स्टेट से, स्टेट ऑफ माइंड से गुजरे जिस स्टेट ऑफ माइंड पे आप अभी हो। सो डोंट थिंक सो मच, ठीक है, ऐसा कुछ भी सोचना नहीं है आपको, ठीक है। अभी सिर्फ और सिर्फ यही ध्यान देना है कि अभी जो ये मेरे पास टाइम है, राइट, ये अभी मेरे पास जो टाइम है, वो टाइम को मुझे अपने बेस्ट तरीके से यूज करना है, दैट्स इट, और कुछ भी नहीं सोचना है आपको, ठीक है। ओके, नाउ सी हियर, इन दिस प्रॉब्लम thermal conductivity variation is mentioned, right? Thermal conductivity varies with respect to space. K is equal to A plus Bx, and A or B are positive constant, right? A and B are positive constant, and it is very much clear, if X increases, then K also increases now. If X increases, then thermal conductivity also increases now. Absolutely correct, absolutely correct. If X increases, then K increases, because A and B both are positive constant. Now, if you see this direction, this is your X direction, this is the X direction, right? This is the X direction. And in X direction, now tell me, because this problem is a steady state problem, this problem is a steady state problem, it is clearly mentioned, the problem is a steady state problem. There is no internal heat generation. In this lab, there is no internal heat generation. So simply, the rate of energy in is equal to rate of energy out. The rate of energy in is equal to rate of energy out, whatever the energy in is equal to energy out. So energy in, that is in the form of conduction, that energy out in the form of the conduction. So I can say the conduction heat transfer is not a function of x now. Conduction heat transfer is not a function of x now, because whatever the conduction in, conduction out, conduction in, conduction out. So conduction is not a function of x. The area normal to direction of conduction heat transfer, area normal to direction of conduction heat transfer, that is also not a function of x. So here the temperature is T naught, here the temperature is 0. So this is the direction of conduction heat transfer, and the conduction heat transfer is not a function of x. Area which is normal to direction of conduction heat transfer, that is also not a function of x. So we can say the flux is also not a function of x. So if you see the Fourier law of heat conduction, if you see the Fourier's law of heat conduction, Fourier's law. So from the Fourier law of heat conduction, we can write this is minus q dot k into dt by dx. Now see here. Now see. The q dot is constant. Q dot is not a function of x. This is constant. This is constant. So simply we can write the product of k dt by dx is constant. The product of k and dt by dx is constant. Product of k and dt by dx is constant. Now, if k increases, then what about the dt by dx? If k increases, then what about the dt by dx? Because the product of k and this dt by dx is constant. So if one increases, automatically other decreases. So if k increases, then automatically this dt by dx decreases. Dt by dx decreases. I hope you can understand this. Right. Now see, in x direction, if you are moving in the x direction, thermal conductivity increases now, because this is A and B are positive. So x increases, k increases. So what about dt by dx? The dt by dx decreases. The dt by dx is decreases. Now dt by dx decreases. Now come to the options. That option number A. In option number A, dt by dx is constant now. In option number 8, the dt by dx is constant. This is the linear, na? This is linear. So option number 8, dt by dx is constant. Now, come to the option number B. If you see the option number B, and in the option number B, if you draw the slope here, let us consider this is the slope, right? Dt by dx, let us consider this is the theta 1 here, and let us consider this is the theta 2 here. And theta is nothing but the dt by dx only. that theta is nothing but the dt by dx only. Theta is nothing but the dt by dx only. So in this graph, the dt by dx decreases. In x direction, x increases, dt by dx decreases. And this is required, right? X increases, dt by dx decreases. So correct option is option number B. Correct option is option number B. If you see the option number C, right? If you see the option number C, in option number C, if you see the dt by dx is there, that means slope here. Here the slope is, this is theta. And what is the slope here? This is a slope. Here the slope increases, x increases. In this graph, x increases, the slope increases, dt by dx is increases. So this is not required. Option C eliminated. Now come to the option D. Option D is only for creating 4 options. So what is the correct option? Option number B. Correct option is option number B. So this is the qualitatively graphs, right? These are the qualitatively plots. These are the qualitative plots. And if I ask you in the same problem, if I ask you, right, this is a qualitatively, right? These graphs are qualitatively graphs. And if I ask how the temperature changes with respect to x, in the same problem, if I ask how the temperature changes with respect to x, in the same problem, if I ask how the temperature changes with respect to x, this is a question. That my option is, option A is linear, option B is cubic, option C is logarithmic, and option D is hyperbolic. How the temperature changes with respect to x in the same question. What is your answer now? Yes, absolutely correct. That correct option is logarithmic. Now if you see the Fourier law of heat conduction, the q dot is equal to, this is minus Ka dt by dx, right? And k is a function of x. So if you separate the variables, k is a function of x and this is minus a dt, right? And how the thermal conductivity changes, with respect to x, that is linear. So this is a plus bx dx, and this is minus a, and this is dt. So if you integrate, so q dot is not a function of x, right? And what is the integration of this? This is ln, right, or x1 to x2, t1 to t2, right? So, and this is 1 upon b ln a plus bx, right? What is the limit? The limit is x1, x2. Area is minus a, and this is t2 minus t1. So how the temperature changes with respect to x? The temperature changes, right? How the temperature changes with respect to x? Temperature changes logarithmically. So correct option is option C. The correct option is option C. Okay, now, right, this is a straightforward question. Considering a slab of 20 mm thickness, right, this is gate 2024 problem. This is gate 2024 problem. Consider a slab of 20 millimeter thickness. There is a uniform heat generation of 100 megawatt per meter cube inside the slab. Left and right faces of the slab are maintained at 150 degrees Celsius and 110 degrees Celsius respectively. Plate has constant thermal conductivity 200 watt per meter Kelvin. 1D steady state. So this is a problem of one-dimensional steady state uniform heat generation. So this is a standard problem. And for this standard problem, you must remember the formula, right? For this standard problem, you must remember the formula. And what is that formula? Right? This is the left phase, this is the right phase. Left phase temperature is TL, right phase temperature is TR. Right. So what is the formula? The temperature variation with respect to x, and this is the x direction. I'm sorry, this is the x direction. This is the x direction. So left phase is my reference phase. Right. Left phase is the reference phase. So what is the temperature variation with respect to x? That is T of x. T of x is equal to, this is TL plus TR minus TL into x by delta plus this is q dot g by 2k, and this is delta x minus x square. Right. This is a standard formula. You must remember this. If you remember this, you can directly solve this problem. Right. And in this question, the location of maximum temperature is asked. So to get the location of maximum temperature, to get location of maximum temperature. So where the temperature is maximum? Temperature is maximum where dt by dx is 0. Temperature is maximum where dt by dx is 0. So dt by dx is 0. That means this is TR minus TL into 1 by delta plus q dot g by 2k. Now this is delta minus 2x is equal to 0. Now find out the x from here, and that is the location of maximum temperature. Right. So TR value is 110. This is 110 minus this is 150 into thickness. Thickness is mentioned, that is 20 mm thickness. So 0.02 plus uniform heat generation 100 megawatt per meter cube. So this is 100 into 10 to the power 3 watt per meter cube. 2 into k. K value is 200. So this is 2 into 200. And this is delta. Delta value is 0.02 minus 2 into x. And this is equal to 0. Right. One equation, one unknown. One equation and one unknown. You can calculate x. You can calculate x. So in this expression, that x is in meter. So what you are getting? What you are getting? What is the answer? Answer is less than 10 mm. That is for sure. Answer is less than 10 mm. That is for sure. Acha, yes. This is 10 to the power 6. No? This is 10 to the power 6. Megawatt, na? 10 to the power 6. 6 mm. Yes. The correct answer is, this is 6 into 10 to the power 3. 10 to the power minus 3 meters. So x is equal to 6 mm. And can you calculate the maximum temperature? If in a same problem, if maximum temperature is asked, in a same problem, if maximum temperature is asked, in same problem, if maximum temperature is asked, maximum temperature. So can you calculate the maximum temperature? Yes, we can calculate the maximum temperature. So put this x is equal to 6 mm here. Right, put x is equal to 6 mm in the temperature variation expression. So at x is equal to 6 mm, T becomes T max. Right, at x is equal to 6 mm, T becomes T max. Right, so you can find out the maximum temperature also. Now see this question. 4 बजे से इंजीनियरिंग मैकेनिक्स का लेक्चर है। तो अभी तो टाइम है ना, अभी तो टाइम है। ट्राई दिस क्वेश्चन। Okay, what is the critical thickness in this problem? The critical thickness is a 10 millimeter dia electrical conductor is covered by an insulation of 2 mm thickness. Okay. So 10 mm dia electrical conductor, that means radius is 5 mm, and this is insulated by an insulation. So this is insulation, correct. And in this question, what is the critical radius? The critical radius is, this is Ki by, this is H naught. Right. So what is the critical radius? Critical radius is 8 mm. Correct. Critical radius is 8 mm. So the Ki thermal conductivity of the insulation 0.08. This is 0.08. 0.08 and H value is 10 and multiplied by 1000. So this is in millimeter. So this is 8 millimeter. Correct? Na? This is 8 millimeter. Right? Critical radius is 8 millimeter. This is correct. 8 millimeter is correct. Critical radius is correct. Na? 8 millimeter. Now, see here. This is 5 mm. Right? This is 5 mm. And this thickness is 2 mm. Correct? Na? Thickness is 2 mm. So this is 7 mm. Right? Let us consider this is the Ri. This is the R0. So R0 is 7 mm. Ri is 5 mm. So if you see the graph, Q dot versus critical radius of or radius of insulation, sorry. So this is the graph. At R is equal to RC, heat transfer is maximum. This is Q dot max. Right. So R naught is 7 mm. R naught is 7 mm. So that means somewhere here. This is 5 mm. This is 7 mm. Right. This is 5. This is 7 mm. Now addition of further insulation. Right. Addition of further insulation of the same material will be. Now see here. If you added insulation further, so the heat transfer increases. Reaches maximum value and then it start to decrease. And then it start to increase. So if you add further insulation, so heat transfer increases the heat loss to a maximum and then decreases the heat loss. So what is the correct option? That option is correct. Option is option C. That option C is correct. Option C is correct. Correct option is option C. Correct option is option C. Option C is correct. Now see the next question. A small metal bed, radius 0.5 mm, initially at 100 degrees Celsius. When placed in a stream of fluid of 20 degrees Celsius, attains a temperature of 28 degrees Celsius in 4.35 seconds. The density and specific heat of the metal are 8500 kg per meter cube and 200 joule per kg Kelvin respectively. If the bed is considered as a lumped system, the convective heat transfer coefficient between the metal bed and the fluid stream is. So this is the problem of unsteady state conduction, and in question it is clearly mentioned. In this problem, lumped system is applicable, and in lumped system temperature is only function of time. In lumped system, temperature is only function of time. Temperature is only function of time. And how the temperature changes with respect to time? How the temperature changes with respect to time? So we can say this is T minus T infinitive upon Ti minus T infinitive is equal to e to the power minus HA rho Vc into tau. Right? This is a temperature variation with respect to time. Correct. Now take log both sides. So this is ln T minus T infinitive upon Ti minus T infinitive is equal to, this is minus h into tau upon, right, this is rho c into, now V by A, we can say this is LC. V by A is nothing but the LC. Correct. Now see, in this problem, the small metal bed, so that is spherical in shape, radius is 0.5 mm. Right, radius is 0.5 mm. So what is LC? That LC is R by 3. That LC is R by 3. That LC is R by 3. Correct. And the initial temperature is 100 degrees Celsius. So this is Ti. And T infinitive is 20. So 100 minus 20. So this is ln. This is 100 minus 20. Now at a time 4.35 second, temperature is 28. So 28 minus 28 minus 20. And that is minus h. Tau value is 4.35 second. This is 4.35 into density. Density is 8500. 8500 into specific heat. That specific heat value is 400 joule per kg Kelvin into LC is R by 3. So R by 3. Now 3 is here. R value is 0.05. Sorry, 0.5. So this is 0.5 into 10 to the power minus 3. Now in this equation there is one unknown, and that unknown is मैकेनिक्स की क्लास 6 से है, 4 से नहीं है. Okay. What is the value of h? Now tell me, what is the value of h? Mechanics class is at okay. Not good. Now tell me what is the value of h? What is the value of h? That B for Bombay. So that is 299.8. 299.8. 299.8 watt per meter square Kelvin. Everyone getting this answer? Everyone getting this answer? 299.8 watt per meter square Kelvin. Yes. So correct option is option B. Option B is correct. Okay. Now come to the next question. This is K2010. This is gate 2010 problem. Now see this question. This problem is related with the fins. A fin has 5 mm dia, 100 millimeter length. Thermal conductivity of fin material is 400 watt per meter Kelvin. One end of the fin is maintained at 130 degrees Celsius and its remaining surface is exposed to the ambient air, which is at 30 degrees Celsius. Convective heat transfer coefficient is 40 watt per meter square Kelvin. The heat loss from the fin is, what is the heat loss from the fin? So length of the fin is mentioned and the diameter of the fin is mentioned. This is the pin fin. Na? Pin fin means circular cross section fin. Pin fin means circular cross section fin. Circular cross section fin. So fin is like this. This dimension is 5 mm and this dimension is 100 mm. Okay. Now whenever the length of fin is mentioned, so what is the first thing? Fin के formula में confusion हो जाता है. Let's see. So whenever you are getting the length of the fin, right? Whenever in a problem length of the fin is mentioned, so what is the first thing that you are doing? What is the first thing? First find out this fin is considered as a short fin or long fin? Right, whenever in a problem length of the fin is mentioned, if in a question it is not mentioned this is a long fin or short fin, if in a question it is not mentioned fin is a long fin or short fin, so what is the first thing that you have to do? That is find out this fin is considered as a short fin or long fin. So for that, first calculate the m into l. First calculate m into l. So if m into l is less than or equal to 5, or ml is considered greater than or equal to 5, that fin is considered as an infinitely long fin. And if m into l product is less than 5, then that is considered as a short fin. In this problem also length is mentioned. So first calculate the m into l. First calculate the m into l. Now calculate m into l. So what is the m? That m is root over HP by KAC. And what is P by AC? The P by AC, this is spin fin. So simply this is nothing but the P pi into D, and this is pi by 4 D square. So this is 4 by D. This is 4 by D. So simply we can write this is 4H upon 4H upon KD. 4H upon KD. So find out m into L. Find out m into L. Right, so this is root over 4 multiplied by that H. H value is 40 watt per meter square Kelvin. Right, K value is 400 into D value is 0.005. So this is m value. And what is the length? Length is mentioned 0.1 meter. So tell me what is m into L. Tell me what is m into L. Tell me what is m into L. M into L. What is m into L? Less than 5 or greater than 5? Less than 5 or greater than 5? I think in this question it is less than 5. I think in this question it is less than 5. Since it is less than 5. Since it is less than 5. So that's why this is short fin. Right. This is the short fin. Short fin. Short fin. Short fin. Now in short fin there are two conditions. One is the insulated tip, other one is the insulated tip, and another one is the uninsulated tip or non-adiabatic tip. In this question it is not mentioned. In this question one end of the fin is maintained at 130 degrees Celsius and its remaining surface is exposed to the ambient air at 30 degrees Celsius. Okay, in this question it is not mentioned the tip is insulated or uninsulated. It is not mentioned in this problem. Right. So consider that is uninsulated tip. If it is not mentioned, if it is nothing is mentioned, then take that is normal case, that is uninsulated tip. So short fin, uninsulated tip or non-insulated tip or non-adiabatic tip. Non-adiabatic tip. Non-adiabatic tip. That means we are assuming from the tip also heat transfer occurs. Right. So short fin, non-adiabatic tip. In case of the short fin non-adiabatic tip, what is the rate of heat transfer from the fin? That is root over HP KAC theta B, and this is tan hyperbolic m into LC. And what is the LC? That LC is the corrected length. LC is the corrected length. So this is L plus. In case of the pin fin, it is D by 4. So actually, if you see here, D is nothing but the 5 mm, right? D is nothing but the 5 mm, and what is the actual length of the fin? That is 100 mm. So there is not much difference between the LC and L, right? So we can say that LC is approximately equal to L. LC is approximately equal to L. So you can use this ml value, whatever you are getting the ml value, you can use that also, no issue. Because This is LC is L plus D by 4. The D is 5 mm. The D is 5 mm. And D is 5 mm. So this is 5 by 4. L is 100 mm. So LC is approximately equal to L. Clear? Right. So that Q dot from the fin, that is root over, that H value is 40. H value is 40. This is pi into D. This is 0.005 into, right, K value is 400 into, this is pi by 4 into D square 0.005 square into theta B. That theta B is nothing but the TB minus T infinitive. And the base temperature is, this is base temperature. This is base temperature and this is T infinitive. So this is 130 minus 30. Right, 130 minus 30. And this is 10 hyperbolic. I already told you LC is approximately equal to L. So 10 hyperbolic ml. So whatever you are getting ml value that you are getting 0.8944. 0.8944. So 0.8944. Put here 0.8944. Now tell me what is the rate of heat transfer through the fin. Right, so this is 4.9. Yes, it is approximately equal to 5. Yes, it is 5. So this is 5 watt. This is around 5 watt, 4 point something. So that is around 5 watt. Yes, so correct option is option B. That option B is correct. Okay, now see the next question. This is also a gate problem. I think this is also gate 2022 problem. Gate 2021, I think. This is gate 2021. This is gate 2021 problem. Gate 2021 problem. Now see here, an uninsulated cylindrical wire of radius 1 mm produces electric heating at the rate of 5 watt per meter. The temperature of the surface of the wire is 75 degrees Celsius when placed in air at 25 degrees Celsius. When the wire is coated with PVC, of thickness 1 mm, the temperature of the surface of the wire reduces to 55 degrees Celsius. Assuming that the heat generation rate from the wire and the convective heat transfer coefficient are same for both uninsulated wire and the coated wire, the thermal conductivity of the PVC material is. So actually there are two cases. One is the uninsulated wire case and second one is the coated wire case. So whenever you are getting two cases, right, whenever you are getting two cases, so make a column like this and write the data related to the case number 1 here, case number 1 here, and write the data related to the case number 2 here. Right, related to the data in two cases. Now case number 1. So case number 1, that is the uninsulated wire. Case number 1 is the uninsulated wire case. Uninsulated wire case. And case number 2 is coated wire case. Coated wire case, or you can say insulated wire case. coated wire case. Coated wire case. Right, now this is uninsulated wire. So let us consider this is a cross section of uninsulated wire. This is a cross section of uninsulated wire. Now see, so the radius is 1 mm, right? Uninsulated cylindrical wire, radius 1 mm to produce electric heating at the rate of 50 watt per meter. Okay, so radius is 1 mm, radius is 1 mm, and heat generation per unit length, that is mentioned 50 watt per meter. 50 watt per meter. Okay, now the surface temperature in this case, that is 75 degrees Celsius. In this case, what is the surface temperature? That is 75 degrees Celsius. So surface temperature, this is 75 degrees Celsius, and what is the ambient temperature? That is 25 degrees Celsius. 25 degrees Celsius, this is the ambient temperature. You can say this is T infinitive. Okay, so this much information we have related to the case number 1. Now come to the case number 2. When the wire is coated with the PVC of thickness 1 mm, okay, in the same wire, now PVC insulation is used. In the same wire, PVC insulation is used. So let us consider this is the PVC insulation and this is the wire. And what is the thickness? Thickness of insulation, that is mentioned 1 mm. Thickness of insulation, that is 1 mm. This is 1 mm. So if I say this is the R1, if I say this is the R1, and if I say this is the R2, can anyone tell me what is the R1, what is the R2? What is the R1? That R1 is nothing but the 1 mm. And what is the R2? That R2 is 1 plus 1, that means it is 2 mm. Correct, na? Convective heat transfer coefficient is H. T infinitive, that is same as the case number 1. This is 25 degrees Celsius. Now, surface temperature reduces, that is to 55 degrees Celsius. So in this case, this surface temperature, this is 55 degrees Celsius. Fine. Heat generation rate from the wire and the convective heat transfer coefficient are same for both the case. So in these two cases, in this case, what is the Q dot by L? That is 50 watt per meter. And what is the H? That H is same as this case. So can you calculate H from this case? Can you calculate H from this case? See, whenever you are getting two cases now, then definitely the data related to the one case is used in the another case, or data related to the one case is used in the second case, or vice versa. Always remember this point. So in this problem, or in this case, H is not mentioned, but in this question it is clearly given the value of H and the heat generation per unit length is same for both the case. So can you calculate H from this case? Can you calculate H from this case? Yes, we can calculate. So if you apply the convection heat transfer, if you apply the Newton's law of cooling, simply we can write this is nothing but the Q dot is equal to this is H into A, and this is Ts minus T infinitive. And what is A? So this is Q dot is equal to H into this is 2 pi R into L, and this is Ts minus T infinitive. Right, now Q dot by L, this is mentioned in the problem, this is H into this is 2 pi R and Ts minus T infinitive. Can anyone tell me what is the H? Because Q dot by L, this is given 50, this is H into this is 2 pi into L. What is the into R? R is 1 mm, so this is 0.001 into Ts value is 75 into 25. So can anyone tell me what is the value of H? Tell me what is the value of H from case number 1. What is the value of H? What is the value of H? 159.15. Yes, absolutely. 159.154 watt per meter square Kelvin. So what is the value of H here? That is 159.154 watt per meter square Kelvin. This is the value of H. This is the value of H. This is the value of H. And once you know the value of H, now see, you know the temperature here, you know the ambient temperature, draw the thermal circuit. So this is the conduction resistance offered by the insulation material, and this is outside convection resistance. This temperature is Ts dash, you can say. This temperature is T infinitive. This is the conduction resistance offered by the insulating material. So this is ln R2 by R1 divided by, this is 2 pi Ki into L, insulation material thermal conductivity, and this is outside convection resistance. So this is 1 upon H. This is 1 upon H into, this is 2 pi R2L, right? And whatever the heat is generated here, that is, whatever the heat generation is there, that is equal to the heat transfer here, right? So if you apply, if you write that Q dot, so Q dot is equal to, this is Ts dash minus T infinitive upon, this is the conduction resistance of the insulation material, and this is outside ambient resistance. Fine. Now Q dot, so Q dot is equal to, now Ts dash, is mentioned, that is 55. This is 55 minus T infinitive. T infinitive is same as the previous case, that is 25 into. Now do one thing, take 1 by L common from here, and or do one thing, 2 pi L, take 2 pi L common from the denominator. So this is 2 pi L upon ln R2 by R1. This is ln R2 by R1 divided by, this is Ki plus ln R2 by R1 Ki upon 1 upon H R2. Now one equation, one unknown. Q dot by L, this is given 50 is equal to 55 minus 25, this is 30 into 2 pi upon ln R2 is 2 by 1, Ki is unknown, plus 1 upon H is 159.154 into R2 value is 0.002. Now tell me one equation and one unknown, and that is Ki. That is the thermal conductivity of the insulation material. Now tell me what is the thermal conductivity of insulation material. What is the thermal conductivity of PVC? That means insulation material. What is the answer? Anyone? 0.2727. 0.2727. I'm getting 1.103. Anyone getting this? Anyone? 1.103 watt per meter Kelvin. Anyone getting this answer? 1.103. Yes, 1.103. Yes, absolutely. 1.103 watt per meter Kelvin. Yes, this is the correct answer. 1.103 watt per meter Kelvin. So I hope you can understand this problem. This is a good problem. I hope you can understand this. Okay, now come to the next problem. Okay. Come to the next problem, gate 2022 problem. Consider a hydrodynamically and thermally fully developed steady fluid flow of 1 kg per second in a uniformly heated pipe with diameter of 0.1 meter and length of 40 meter. So this is a problem related with the internal force convection, because in this problem mass flow rate is mentioned. So this is the problem of internal force convection problem. So consider a hydrodynamically and thermally fully developed steady fluid flow of 1 kg per second in a uniformly heated pipe with a diameter 0.1 meter and length of 40 meter. Constant heat flux condition is applied. Right, constant heat flux condition is there. So constant heat flux 15,000 watt per meter square is imposed on the outer surface of the pipe. The bulk mean temperature of the fluid at the entrance to the pipe is 200 degrees Celsius. Reynolds number is mentioned, Prandtl number is mentioned, and fluid properties are also mentioned. Nusselt number relation is given. The pipe surface temperature at the exit. Pipe surface temperature at the exit. So first draw a rough diagram. So whenever you are getting problem, try to draw a rough diagram like this. So there is a pipe, and this pipe is subjected to the constant heat flux condition. And flux is mentioned, constant heat flux condition, and flux value is 15,000 watt per meter square. 15,000 watt per meter square Kelvin. 15,000 watt per meter square. Mass flow rate is 1 kg per second. Mass flow rate is 1 kg per second. And length is 40 meter. This length is 40 meter. This length is 40 meter. The bulk mean temperature of the fluid at the entrance to the pipe. Entrance to the pipe, that means here. TMI is given. So bulk mean temperature of the fluid at the inlet is TMI, and at the exit, that is TME. So what is the TMI? The TMI is mentioned 200 degrees Celsius. TMI is 200 degrees Celsius. And TME is unknown. TME is unknown. For this problem, Reynolds number is mentioned, and that is 8500. Reynolds number value is 8500. Prandtl number value is also mentioned, that is 5. Fluid properties are given. The pipe surface temperature at the exit. Pipe surface temperature at the exit. So what is the pipe surface temperature at the exit? So let us consider TSE. Right. Let us consider TSE is the pipe surface temperature at the exit. TSE is the pipe surface temperature at the exit. Just 1 minute. Just 1 minute. Okay, so let us consider the surface temperature at the exit is TSE. This is unknown. We have to calculate this TSE. That means in a question TSE is asked, not TME. And for calculation of TSE, you must know the TME. TME is the fluid temperature at the exit, bulk mean temperature of the fluid at the exit, and TS is the surface temperature at the exit. Right? Now see, if you apply, because this is a constant heat flux condition. This is a constant heat flux condition. So if you apply the Newton's law of cooling at the exit, so we can write that Q dot is equal to, this is H into, right, TSE minus TME. The Q dot is equal to H into TSE minus TME. What is the TSE? That is the surface temperature at the exit. And what is the TME? That is a fluid bulk mean temperature at the exit. Q dot is the heat flux. H is the convective heat transfer coefficient. So if you see this equation, Q dot is known. Right? If you see this equation, Q dot is known. TSE we have to calculate. TME is unknown. For calculation of TSE, TME is required. And H is convective heat transfer coefficient, that is also required to calculate the for the calculation of TSE. So TSE is equal to, we can write that TSE is equal to, this is Q dot by H plus this is TME. Now Q dot is known. Now focus for calculation of H. So for calculation of H, Nusselt number relation is mentioned. For calculation of H, Nusselt number relation is mentioned, and Nusselt number relation is, that is 0.023 into Reynolds number to the power 0.023, Reynolds number to the power 0.8, and Prandtl number to the power 0.4. This is the Nusselt number relation. And Nusselt number we can write, this is H d by Kf. So from this relation we can calculate H. H into diameter is 0.01 meter. Diameter is 0.01 meter. Kf, thermal conductivity of the fluid, that is mentioned 0.08 watt per meter Kelvin, is equal to, this is 0.023 into Reynolds number value is 85,000 to the power 0.8, and Prandtl number value is also given in the problem, and Prandtl number to the power 0.4. So can you calculate H from here? What is the H? Can you calculate H from this relation? Can anyone tell me what is the value of H? Can anyone tell me what is the value of H? Can anyone tell me? Now once you know the H, now focus on calculation of TME. So for calculation of TME, apply the energy balance. For calculation of TME, apply the energy balance. Now this is your system. This is the system. This is the system. So if you apply the energy balance, simply you can write, this is a steady state problem. So if you apply the energy balance, energy balance, simply we can write the rate of energy in is equal to rate of energy out. There is no heat generation, and that is a steady state problem. So whatever the energy in is equal to energy out. Now tell me what is the energy in. So that energy in, enthalpy rate in, so we can write this is the m dot Cp Tmi, this is in, plus what is the in, the q dot multiplied by surface area. What is the out, enthalpy rate out, and that is m dot Cp, that is Tme. So simply we can write that q dot into surface area, or simply this is pi into d into L is equal to, this is m dot Cp and this is Tme minus Tmi. Now can you calculate Tmi? Can you calculate Tme from here? Tme. So q dot is 15,000 pi into, what is diameter? Diameter is 0.1 into this is 40. Mass flow rate is also mentioned, that is 1 kg per second. Specific heat is 2600 joule per kg Kelvin, 2600. Tme is unknown, now Tmi is 200. Correct, na? Tmi is 200. Tmi is 200. Now can anyone tell me what is the Tme? Can anyone tell me what is the Tme? What is the Tme? Tme is 272.49. Okay, Tme is 272.49. Tme is 272.49 degrees Celsius. So this is the Tme. You can calculate H from here. Now anyone tell me what is the value of H? What is the value of H? And once you know the H, see, once you know the H, once you know the Tme, you can calculate the Tse, because q dot is known. So Tse is equal to Tme plus, right, Tse is equal to Tme plus, this is q dot by H. So this is 272.49 plus, this is 15,000 divided by that value of H. That value of H, put the value of H here and you can calculate Tse. What is the value of H? What is the value of H? What is the value of H? Can anyone tell me what is the value of H? H is 37.56. H is 37 point, this is 307.56 watt per meter square Kelvin. Now what is Tse? Tse is 321.26. 321.26 degrees Celsius. This is the Tse. Okay, if I ask you what is the TSI? What is the surface temperature at the inlet? Can anyone tell me? If I ask you what is the surface temperature at the inlet? Surface temperature at inlet. If I ask you what is the surface temperature at the inlet? TSI. Surface temperature at the exit, this is 321.26 degrees Celsius. Now if I ask you what is the surface temperature at the inlet? Can anyone? What is the surface temperature at the inlet? What is the logic? What is the concept to calculate the TSI? What is the logic? What is the concept to calculate the TSI? What is the logic? So in question it is clearly mentioned the flow, this is the problem of hydrodynamically and thermally fully developed flow. Right. So in case of fully developed flow, for fully developed flow, for thermally fully developed flow, for fully for thermally fully developed flow. So there is a one method to calculate the TSI. The Q dot is equal to, we are applying the Newton's law of cooling at the exit. Similarly, you can apply the Newton's law of cooling at the entry. So Q dot is equal to H TSI minus TMI. So this is the one way to calculate the TSI. Another way, for thermally fully developed flow, we know that this Ts minus Tm is constant. The Ts minus Tm is constant. Right, Ts minus Tm is constant. Now Ts minus Tm is constant. So Ts minus Tm at inlet, Ts minus Tm at inlet is equal to Ts minus Tm at the exit. Right. Now Ts minus Tm at the inlet. So Ts I. Now what is the TMI? The TMI is 200 is equal to, now TSE we already calculated. TSE we already calculated, that is 321.26 minus TM. TM at exit, that we already calculated, na? 272.49. 272.49. Right. Now calculate TSI from here. You can calculate TSI by using this concept also. You can calculate TSI by using this concept also. Right. 248 point. Yes. So always remember this concept. Right. Ts minus Tm is constant for constant heat flux condition in thermally fully developed region. For constant heat flux condition in thermally fully developed region, Ts minus Tm is constant. Okay, now see the next question. This is gate 2021 problem. Gate 2021 problem. So the ambient air flows over a heated slab having flat top surface at y is equal to 0. The local temperature profile within the thermal boundary layer is given by 300 plus 200 e to the power minus 5y, where y is the distance measured from the slab surface in meter. Thermal conductivity of air is 1 watt per meter Kelvin and that of the slab is 100 watt per meter Kelvin. Then the magnitude of temperature gradient within the slab at y is equal to 0 in Kelvin per meter. So we have the heated slab like this. We have the heated slab like this. So this is the heated slab. Right, this is the slab. And air is flowing over this heated slab. Thermal conductivity of the air is mentioned. Thermal conductivity of air is mentioned. That means Kf is mentioned, that is 1 watt per meter Kelvin. And y is distance measured from the slab surface. Okay. So this is the x direction and this is the y direction. This is the x direction and this is the y direction. So in a fluid side, the temperature variation, the temperature variation is given. Right, in fluid side, the temperature variation is given. and that temperature variation is T of y is equal to 300 plus 200 e to the power minus 5y. So if you apply the energy balance here, 10, yes, absolutely correct, 10. If you apply the energy balance, if you apply the energy balance at interface, so we can say this is minus kf into dt by dy at y is equal to 0 on fluid side is equal to minus ks dt by dy at y is equal to 0 slab side. Right, so fluid side temperature variation is given with respect to y. Now we can calculate dt by dy. So that dt by dy, right, that is 200 minus 5 e to the power minus 5y. Now dt by dy at y is equal to 0 fluid side. So that is, right, that is 200 minus 5. Right, so kf value is minus cancel out. Kf value is 1 into, this is minus 1000 is equal to ks value is 100. Now dt by dy at y is equal to 0 slab side, this is the unknown. This is unknown. dt by dy at y is equal to 0 on fluid side, solid side, that is unknown. Right, so 100 and 100 is 100. So magnitude is asked, right? Magnitude dt by dy at y is equal to 0 slab side. Magnitude is asked. So this is nothing but the 10 Kelvin per meter. This is nothing but the 10 Kelvin per meter. So this is a simple problem based on the energy balance. Simple problem. Now see the next question. A thin vertical flat plate of height L and infinite width perpendicular to the plane of the figure is losing heat to the surrounding by natural convection. The temperature of the plate and the surrounding and the properties of the surrounding fluid are constant. Relationship between the average Nusselt number and the relief number is given as. So Nusselt number relation with relief number is mentioned. That Nusselt number is equal to k into relief number to the power 1 by 4. K is constant. The length scale for Nusselt number and relief number are the height of the plate. The height of the plate is increased to 16 L, keeping all other factors constant. If the average heat transfer coefficient for the first plate is H1, then that for the second plate is H2. So what is the value of H1 by H2? This is the question. Okay, and this is the vertical plate. So in this problem, it is clearly mentioned the Nusselt number is directly proportional to relief number to the power 1 by 4, and relief number is the product of Grashof number and Prandtl number, right? So if the height of the plate changes, the Prandtl number does not change, right? If you change the height of the plate, right, initially it is L, then it is 2 times of L, right? Initially it is L, then it is 2 times of L. Grashof number, definitely it will changes because it depends on the characteristic length, but the Prandtl number is independent on the characteristic length, so it is constant. So directly we can say Nusselt number is directly proportional to Grashof number to the power 1 by 4. Okay. Now see the Nusselt number, this is HLC by KF, and Grashof number, this is G beta LC cube, this is Ts minus T infinitive upon nu square. Right. Now if you see this expression, then we can write Nusselt number, this is the HLC by KF, directly proportional to. Now Grashof number. So if you see the Grashof number, remaining parameters are constant except the LC. So we can write this is LC to the power, this is 3 by 4. LC to the power 3 by 4. Correct, na? Because other parameters are constant. G is constant, beta is constant, this is constant, this is constant. The only change that occurs in the LC, because LC, initially LC is L, now it is now it is 16 times of L, I think 16 times of L. Yes, fine. Now see, this KF is also constant. Fluid properties are not changing, so we can write that H is directly proportional to, this is L C to the power 3 by 4 L C to the power 3 by 4 minus 1. We can write that H is directly proportional to L C to the power, this is minus 1 by 4. Right. So H1 by H2. What is the H1 by H2? That is LC1 by LC2. H1 by H2 is LC1 by LC2 to the power minus 1 by 4. So H1 by H2. Now this is L, and this is 16 times of L minus 1 by 4. So L and L is cancel out. So this is H1 by H2. This is 1 upon 2 to the power 4 minus 1 by 4. 4 and 4 is cancel out. So H1 by H2 is 2. Right, that H1 by H2 is equal to 2. So correct answer is H1 by H2 is 2. This is the correct answer. Okay, now see the next question. This is GATE 2024 problem. Okay, try to solve this question. In question, effectiveness of heat exchanger is asked. So there is a condenser type of heat exchanger, correct na? The condenser is a shell and tube. The condenser is a shell and tube heat exchanger which consists one shell and 20,000 tubes. Water flows through each tube is at a rate of 1 kg per second. So the total mass flow rate of the water is 20,000 kg per second. And inlet temperature is given, that is 30 degrees Celsius. Steam in the condenser shell condenses at the rate of 430 kg per second at a temperature of 50 degrees Celsius. If the heat of vaporization is 2.326 megajoule per kg and specific heat of the water is 4 kilojoule per kg Kelvin, then what is the effectiveness of heat exchanger? What is the answer that you are getting? Anyone? So this is a condenser type of heat exchanger, and whenever there is a phase change heat exchanger, the relative direction of fluid is immaterial. So this is a steam which condensate, and this temperature is T saturation, or you can say the hot fluid inlet temperature, hot fluid exit temperature, that is equal to T saturation, and that is mentioned. What is the temperature? 50 degrees Celsius. That temperature is 50 degrees Celsius. Right, and cold fluid is a water. So water of heating of cold fluid occurs. So cold fluid inlet temperature is TCI and exit temperature is TCE. The cold fluid inlet temperature is 30 degrees Celsius. This temperature is 30 degrees Celsius. Correct. Exit temperature is not given. Okay. Now, what is the mass flow rate of the mass flow rate of the cold fluid? So in one tube, the mass flow rate is 1 kg per second, and there are 20,000 tubes. So what is the mass flow rate of the cold fluid? So mass flow rate of the cold fluid is, this is 20,000 kg per second. 20,000 kg per second. And the mass flow rate of steam or hot fluid. Steam is a hot fluid. Mass flow rate of hot fluid is 430 kg per second. 430 kg per second. The latent heat of vaporization, that is HFG, that is 2.326 into 10 to the power 6 joule per kg. And specific heat of the water, that means cold fluid, that is 4 into 10 to the power 3 joule per kg Kelvin. Right. So what is the effectiveness? That effectiveness is, That effectiveness is actual heat transfer to maximum possible heat transfer. Actual heat transfer to maximum possible heat transfer. Now what is the actual heat transfer? So simply we can say, right, the mass flow rate of steam is mentioned, latent heat of latent heat is also mentioned. So if I say that actual heat transfer, if you apply the energy balance for condenser type of heat exchanger, so we can write this is m dot c of cold fluid exit temperature minus cold fluid inlet temperature is equal to mass flow rate of hot fluid into latent heat of condensation, that is also equal to u into theta m, where theta m is LMTD. Right, so this is actual heat transfer. So actual heat transfer is nothing but the m dot h into HFG. Correct. Now what is the maximum possible heat transfer? So maximum possible heat transfer, to get maximum possible heat transfer, this is the minimum heat capacity rate into hot fluid inlet temperature minus cold fluid inlet temperature. And the minimum heat capacity rate is for the water, because in this case, what is the maximum heat capacity rate? The maximum heat capacity rate is for the steam. Maximum heat capacity rate is infinite, and that is for the steam. So minimum heat capacity rate is for the water. So minimum heat capacity rate is for the water. So we can write that m dot h is 430 into this is 2.326 into 10 to the power 6 divided by m dot minimum, that is nothing but the for the cold fluid. So this is 20,000 into specific heat 4 into 10 to the power 3 into hot fluid inlet temperature 50 minus 30. Now tell me, what is the effectiveness? Is it clear to everyone? Is it clear or not? Is it clear or not? What is the specific heat during the phase change? What is the specific heat during the phase change? What is the specific heat during the phase change? That specific heat during the phase change is infinite now. Specific heat during the phase change is infinite now. Infinite. So phase change occurs for the steam now. So for steam, what is the specific heat? That specific heat is infinite. So specific heat is infinite for the steam. So definitely the heat capacity rate is also infinite. So what is the if you consider these two fluid, then what is the minimum heat if you consider these two fluid, then for which fluid the heat capacity rate is minimum and for which fluid the heat capacity rate is maximum? So for the water the heat capacity rate is minimum and for the steam the heat capacity rate is maximum, and that is equal to the infinite. Is it clear or not? Is it clear or not? 0.625. Everyone getting this? Everyone getting this 0.625. Everyone getting this 0.625. Everyone getting this? Okay, now this is GATE 2022 problem. $20,000 tube concept. See, in this question, the type of heat exchanger is one shell and multiple tubes. One shell, multiple tubes. So how many tubes in this heat exchanger? How many tubes? There are 20,000 tubes. How many tubes? There are 20,000 tubes. 20,000 tubes. And from each tube, what is the mass flow rate of the water? That is 1 kg per second. So what is the total mass flow rate of the water? From the one tube, the mass flow rate of the water is 1 kg per second. So what is the total mass flow rate of the water? The total mass flow rate of the water is 20,000 kg per second. Simple logic. Okay, now come to the next question. This is gate 2022 problem. Gate 2022 problem. Point 424. Anyone? 0.24. That is the one answer that I am getting. Any other? Okay. During open heart surgery, a patient blood is cooled down 25 degrees Celsius from 25 degrees Celsius from 37 degrees Celsius using a concentric tube counterflow heat exchanger. Right. So there is a counterflow heat exchanger. So if you see the temperature variation in counterflow heat exchanger, hot fluid is a blood, and blood is cooled down from 20 blood is cooled down to 25 degrees Celsius from 37 degrees Celsius. So this is a THI and this is a THE. This is blood. By using the water. So what is the cold fluid? Cold fluid inlet temperature, cold fluid exit temperature. This is water. Correct. And this temperature is 37 degrees Celsius. This temperature is 25 degrees Celsius. This temperature is 4 degrees Celsius. And this temperature is 18 degrees Celsius. Point 36. Okay. So in this question, what is asked? Effectiveness. So we know that effectiveness is actual heat transfer to maximum heat transfer, or we can write this is the minimum heat capacity rate into THI minus TCI. Right? Now see here, that actual heat transfer, we know that actual heat transfer is nothing but the m dot c into delta t, m dot c into delta t. So actually the product of m dot c and delta t is constant, right? This is constant. M dot c into delta t, the product of m dot heat capacity rate and delta t is constant. So if this is the minimum, then obviously this is maximum. If this is minimum, then obviously this is maximum, and vice versa, right? Are we right now? If you apply the energy balance, so we write now the actual heat transfer is equal to, this is the heat capacity rate of the cold fluid, then delta T of cold fluid is equal to heat capacity rate of hot fluid into delta T of hot fluid. We can write now, right? So simply if you consider this is the X, this is the Y, right, or X1, Y1, and if you consider this is the X2, this is the Y2, so the product of X and Y is constant. The product of X and Y is constant, so if X increases, then definitely the Y decreases, right? So product of heat capacity rate and delta T is constant. If this is the minimum, then obviously this is the maximum. Now if I write minimum heat capacity rate is, if I write minimum heat capacity rate here, so definitely you must multiply with maximum of delta T hot, delta T cold, right? Now see here, the minimum heat capacity rate is cancelled out from numerator and denominator, so this is cancelled out. Now see here, if you consider delta T of hot fluid, so delta T of hot fluid, this is 37 minus 25, so this is 12 degrees Celsius. If you consider delta T of cold fluid, so delta T of cold fluid, this is 18 minus 4, so that is 14. So delta T of cold fluid is maximum. So definitely for the cold fluid, the heat capacity rate is minimum. Delta T of cold fluid is maximum, so definitely for the cold fluid, the heat capacity rate is minimum, right? So simply you can write this is equal to, this is 14 divided by, now THI is 37, 37 minus 4. This is 37 minus 4, so this is 14 divided by, right, this is 33. Now calculate effectiveness from here. Point 3636. Everyone getting this? 0.3636. Any other answer? This is the final answer, 0.3636. What about that 0.424? What about that? No, this is 0.424. This is right answer. Okay, this is wrong. Na? 0.424. This is correct answer. 0.424 is the correct answer. Okay, is it clear? Okay. Now try to solve this question. So in this question, what is the logic? The temperature T1 of surface 1 of the slab under steady state condition is the temperature T1 of the surface 1, that means this temperature T1. So what is the concept, what is the logic on this question? So the conduction is equal to, here the temperature is T1, here the temperature is T2. So in this slab there is a conduction from bottom surface to the top surface, there is a conduction. And yes, absolutely right. And outer side there is a heat transfer via convection, and there is a heat transfer via radiation. So at steady state, simply you can say, the conduction is equal to, at steady state simply you can say the conduction is equal to convection plus radiation. If you apply the energy balance at the steady state, the conduction is equal to convection plus radiation. Now what is the conduction? The conduction occurs from this surface to this surface. So this is nothing but this is K multiplied by A, and this is T1 minus T2 divided by thickness, and that thickness is, let us consider, that is delta. So this is the conduction from bottom to top of the slab, and this is equal to convection. So convection occurs from the surface to the fluid. So this is H into A, and this is T 2 minus T infinitive, and the radiation occurs between the surface 2 and the surrounding. So simply we can write this is A into epsilon sigma B, and this is T2 to the power 4 minus T infinity to the power T surrounding to the power 4. T surrounding to the power 4. Surrounding temperature is 0 Kelvin. Right, surrounding temperature is 0 Kelvin. Surrounding temperature is 0 Kelvin. So this is 0. Now see, thermal conductivity is given 10. Area responsible for the conduction, responsible for the convection, and responsible for the radiation is same. So 10 multiplied by T1 is unknown, T2 is 300 divided by thickness is 0.2 is equal to H value is 100 into T2 is 300 minus T infinitive is 293 plus emissivity of the surface 2 is 0.5, Stefan's Boltzmann constant 5.67, 10 to the power minus 8, T2 to the power 4, that means 300 to the power 4. There is a one equation and one unknown, that is T1. One equation and one unknown, and that is a T1. Now calculate T1 from here. One equation, one unknown. Now calculate T1 from here. So what is the T1 that you are getting? Uh, 323.18. 323.18. 323.18 Kelvin. 323.18 Kelvin. Any other answer? 319. Okay. Now tell me the exact one, because we have two answers. 323, 319, then there is a 321. 323, 319, then there is a 321. 318.59. 318.59. So that is around 319, correct? Na? 319. 318. Okay. So that is around 319. 319 Kelvin. Okay, so I hope whatever we discussed in today's class, that is clear to everyone. Remaining part we will cover during the Maha revision. Okay. Remaining PYQs we will cover during the Maha revision, and I think that Maha revision for the heat transfer is Saturday. I think so. Remaining part we will cover during the Maha revision session. And Maha revision session is on Saturday. Then there is a Abhyas session on Sunday. So we will cover remaining part on those two sessions. रेडिएशन के क्वेश्चन को समझने में थोड़ा टाइम लगता है, क्यों? रेडिएशन के क्वेश्चन तो देखने से समझ में आ जाता है कि रेडिएशन का क्वेश्चन है. रेडिएशन में दैट इंपॉर्टेंट टॉपिक्स आर, what is a shape factor? One important concept is a shape factor concept, and the second important concept is radiation heat exchange between two bodies. That bodies are radiation heat exchange between two gray bodies or two non-black bodies. These two topics are very very important. ठीक है. एंड अगर कोई ऐसा दिक्कत जा रहा है आपको, सो थोड़ा सा प्रैक्टिस करना पड़ेगा. सी कैसे टाइप के क्वेश्चन आ सकते हैं? देखो अभी क्वेश्चन तो यार देखो, क्वेश्चन में ऐसा नहीं है. आप कैसे टाइप का क्वेश्चन आ सकता है? अभी आप लोगों ने पीवाईक्यूज किए, ठीक है ना? पीवाईक्यूज से रिलेटेड ही आपके पास क्वेश्चंस देखने को मिलते हैं, राइट? इफ यू कंपेयर, let us consider we compare the last year question, gate 2024. So if you see the gate 2024 questions, so in gate 2024 question, there is a one question based on the variable thermal conductivity, right? That we already covered in our class. There is a one question related to the uh, uniform internal heat generation, right? Where the maximum temperature occurs, that we also covered, right? So that is the one question. Same type question we already covered in the classes, right? Then there is a question related to the convection. Then there is a question related to the heat exchanger that we covered, right? That number of tubes question, number of tubes. So similar type के questions आपको देखने को मिलेंगे, ठीक है? If you compare 2 years question, then definitely you will understand कि ऐसा कुछ बहुत ज़्यादा आपको और नहीं करना है, ठीक है? Last time focus on a revision, ठीक है? Focus on only revision, test, revision, test. That's it. हीट ट्रांसफर के लिए सिर्फ नहीं, पीवाईक्यूज के अलावा आपके पास, ठीक है, टेस्ट सीरीज ऑल्सो देयर ना, ठीक है? टेस्ट सीरीज इज ऑल्सो देयर, राइट? सो टेस्ट सीरीज के जो क्वेश्चंस हैं वो आप लगाइए. टेस्ट सीरीज में भी आपको नए क्वेश्चंस मिलेंगे. सो you have PYQ question, you have test series question, right? You have classroom questions, you also have DPP questions. But thing is that कि अभी टाइम कम है, तो इतने कम टाइम में इतनी सारी चीजें कैसे कवर करें? So now focus on the PYQs and some test series questions. That's it. There is no, I can say कि अगर आपके पास टाइम कम है तो there is no need to solve the there is no need to solve the DPPs. ठीक है? There is no need to solve any other questions, right? You have the PYQs, you have the test series question. That's it. लास्ट टाइम पे बस इतना ही कर सकते हो. अगर आपको रिवीजन के लिए करना है तो और कुछ करने की जरूरत नहीं है आपको. Finding difficult to solve connection problem internal. one needs to be concentrated. Okay, see, if you see the internal force convection problem, na, in internal force convection problem there is a similar number of times similar kind of question is asked, number of times similar kind of questions, right? If you go through the PYQs then you can easily understand. ठीक है, तो उसके अलावा कुछ और अलग से करने की जरूरत नहीं है, ठीक है? इन इंटरनल फोर्स कन्वेक्शन प्रॉब्लम यू विल गेट दिस सिमिलर काइंड ऑफ क्वेश्चन, सिमिलर if there is a constant heat flux condition then the surface temperature at the exit is asked, right? If there is a constant void temperature condition is there, so if there is a constant void temperature condition, so what is the temperature at any x, what is the temperature at a exit, such type of question is asked, right? So practice similar kind of question, right? This kind of question this type of question we covered in our classroom, right? And also you will get question also you will get the question in PYQs, right? So practice those questions, right? Actually in convection, okay, if you see the convection wala part, so in convection wala part the questions are similar kind of, right? Number of times similar kind of question is asked, right? So focus on those part, इधर उधर और करने की जरूरत नहीं है आपको. Right, so first go through the PYQs now. First go through the PYQs. If you go through the PYQs, then you can easily understand what I want to say. Okay. Okay, so thank you so much for this session. Remaining part we will do in Maha revision session. So thank you so much. Bye bye. Take care and have a good night, everyone.